Dear students, Namaste. Good morning to you all, and also welcome to another session of our mathematics class. In the previous session, we have discussed the basic concepts of vector algebra, and also we have solved question number 1 to 10 from exercise 10.2. Hope you have revised well. In today's session, we shall discuss the remaining problems from exercise 10.2. Let's move on to the topic. Let's begin with direction cosines and direction ratios. First of all, let's discuss direction cosines. Consider the coordinate axes x, y and z. The point of intersection is marked y, and the position vector OP is also marked. And the position vector OP makes angle alpha with the positive direction of x-axis, and angle beta with the positive direction of y-axis, and gamma with the positive direction of z-axis. And here this looks like the negative direction. Since it is drawn from the z-axis, it is represented like this. Here the direction cosines, in the sense the direction cosines of a vector are the cosines of the angles between the vector and the coordinate axis. So here the cosines of the angles between the vector and the coordinate axis. Here the vector is making angle alpha with the x-axis, angle beta with the y-axis, and gamma with z-axis. So cosine of the angle, in the sense cos alpha, cos beta and cos gamma are the direction cosines, and it is usually represented by the letters L, M and N respectively. So in short, we can say that L is equal to cos alpha, M is equal to cos beta and N is equal to cos gamma are the direction cosines. Suppose here the angles are not given to you, then how will we be able to calculate the direction cosines? So let's calculate that. So here coordinate axis we have drawn, and the point of intersection also I have marked. Then a point pxy and its position vector OP is also drawn. Then this beta portion I am taking because it is easy to explain. So the vector OP makes the positive direction of y-axis an angle beta. So if you complete the right triangle here, the length of this portion is y, because that is a y coordinate, and this OP is the magnitude of the vector OP that we can represent it by r. So by using trigonometric ratio, cos beta is equal to adjacent divided by hypotenuse. Here adjacent is y and the hypotenuse is r. So cos beta we can write as y divided by r. So y is the y-axis value and r is the magnitude of the vector OP. Similar way we can write m is equal to y divided by r. M is the cos beta, m is equal to cos beta, so cos beta we have got as y divided by r, so m is equal to y divided by r we can conclude. Same way we can calculate cos alpha, that is x divided by r, that is L is equal to x divided by r, and cos gamma is equal to z divided by r, we can write it as n is equal to z divided by r. Here we can conclude as L is equal to x by r, m is equal to y by r and n is equal to z by r are the direction cosines. Please note that the coordinates of the point P, here P is written as x, y, z. Here x value we can calculate from here. X is L into r, y is m into r and z is n into r. So the coordinates of the point P we can calculate as LR, MR and NR. X value is LR, Y value is MR and Z value is NR. And also note that L square plus M square plus N square is equal to 1. Here when you square it and calculate, you will get it as x square plus y square plus z square divided by denominator is r square. So r square we know that it is modulus of, or the magnitude of the vector r. Magnitude formula is root of x square plus y square plus z square. When you square it, it comes as x square plus y square plus z square. When you cancel it, numerator and denominator, we will get it as 1. You can try this one in a rough sheet of paper, how we are getting L square plus m square plus n square is equal to 1. Hope it is clear. Next we shall discuss the direction ratios. Any number that are proportional to the direction cosines are called direction ratios, usually represented as A, B and C. So any numbers that are proportional to the direction cosines we have learned L, M and N, or cos alpha, cos beta and cos gamma, and it is usually represented as A, B and C. That is, A is equal to RL, B is equal to RM and C is equal to Rn are the direction ratios. Here R is the magnitude. We have already learned this one. That is R cos alpha and R cos beta and R cos gamma. Here L we know that it is a direction cosine. That is L is called cos alpha and M is equal to cos gamma, cos beta, and N is equal to cos gamma. So R cos alpha, R cos beta and R cos gamma are written. Next, projection of a vector on another vector. Consider a vector B and another vector A, and the projection of vector A on other vector B is given by projection in the sense, suppose if there is a light on top of this A, if you flash a light on top of A, the shadow of vector A falls on this vector B, means something like this. So this particular portion is the projection of vector A. This particular portion is a projection of vector A on this vector B. So this can be calculated as vector A dot unit vector B. Formula is vector A dot unit vector B. Unit vector B in the sense a particular portion from here, one unit, that is the unit vector B. And if you take A vector A dot unit vector B, we will get the projection of vector A on vector B. Here what comes as on the vector, that unit vector we have to take. For example, projection of vector B on the vector A is given by vector B dot unit vector A. So that must be very careful. What comes as on other vector B, on vector, here on vector is B, so that unit vector we have to take A dot vector unit vector B. Or if you substitute that unit vector formula, A dot vector B divided by modulus of vector B. This is the most useful formula because at a stretch we can calculate everything here. So A vector A dot vector B divided by modulus of vector B. This is the formula for finding the projection of a vector A on other vector B. Next we shall discuss the section formula. Let P and Q be the 2 points represented by the position vectors vector OP and vector OQ respectively with respect to the origin O. There is a first case when R divides PQ internally. Suppose there are 2 points P and Q and their position vectors OP and OQ are marked here, and there is a point R which divides P and Q internally in the ratio m is to n. Internally in the sense R must be in between P and Q. R divides P and Q internally in the ratio m is to n. Then the position vector of R or OR is the position vector of the point R which divides P and Q internally in the ratio m is to n is given by OR. Position vector of R is OR. OR is equal to MB plus NA. M into vector B plus N into vector A divided by M plus N. Next is case 2 when R divides PQ externally. The position vector of the point R which divides the line segment PQ externally in the ratio m is to n is given by, let's see the diagram. Here the points P and Q are marked and position vector OP and OQ also marked, and here the point R divides P and Q, PQ externally in the ratio m is to n. External division in the sense the point R is outside of the line segment PQ. So here m is to n is the ratio. So the position vector of OR is vector OR equal to MB minus M into vector B minus N into vector A divided by M minus N. For internal division, the formula is OR. Vector OR is equal to M into vector B plus N into vector A by M plus N. For external division, position vector OR. Vector OR is equal to M into vector B minus N into vector A divided by M minus N. There is a note. If R is the midpoint of PQ, then M is equal to N. The ratio must be same if R is the midpoint of PQ in the sense. And therefore, R is the midpoint of PQ. Then the position vector of the point R, that is vector OR, is equal to A plus B divided by 2. Here M and N are equal. M is to N is 1 is to 1 since R is the midpoint. So vector OR can be calculated by the formula vector A plus vector B divided by 2. Next we shall discuss question number 3 that was pending from exercise 10.2. The question was, write two different vectors having same direction. Same direction in the sense we have to write two vectors which are having the same direction cosines. DCs. Direction cosine short form is DC. DCs we can call. Here the vectors we are taking as vector P is equal to I plus I cap plus j cap plus k cap, and vector Q is equal to 2 I cap plus 2 j cap plus 2 k cap. Here if we multiply a scalar, that is scalar quantity is 2, if we multiply a constant 2 with P, we will get the another vector, or any other constant we can multiply with P, we will get another vector. That two vectors DCs or direction cosines will be same. Let's check it. The direction cosines, we have the formula L is equal to x by r, M is equal to y by r, N is equal to z by r, where r is the modulus. Here the DCs of vector P are L is equal to x divided by modulus of r, that is root of x square plus y square plus z square. So here x is 1. So 1 divided by root of x square plus y square plus z square. X, y, z is 1 here. So x square plus y square plus z square is 1 square plus 1 square plus 1 square. That is equal to 1 divided by root 3. Then m is equal to 1 divided by m, also same only here y value is 1. 1 divided by root of x square plus y square plus z square, we will get as 1 by root 3. And n is equal to n also z divided by z value is 1 here, 1 divided by root of x square plus y square plus z square, that also we will get as 1 by root 3. Now let's check the direction cosines of vector Q, that is L is equal to, here x value is 2, 2 divided by root of x square plus y square plus z square, that is root of 2 square plus 2 square plus 2 square, that is equal to 2 divided by 2 square is 4, so 4 plus 4 plus 4, that is equal to 12. 12 we can write it as 4 into 3. When the 4 comes out of the square root, it comes as 2. So 2 root 3. 2 divided by 2 root 3, and 2 will be cancelled, and 1 by root 3 is the direction cosine of Q, first direction cosine. The next is M is equal to, that is m, y values here 2, 2 divided by root of x square plus y square plus z square, as before the calculation, that is 2 divided by 2 root 3, 2 cancelled, and we will get as 1 by root 3. And n is equal to, here also z value is 2, 2 divided by root of x square plus y square plus z square, same calculation, 2 divided by 2 by root 3, 2 cancel, and finally we will get as 1 by root 3. Here the direction cosines, DCs of vector P and vector Q are same. So we have written two vectors having the same direction, and they are different also. Here vector P is not equal to vector Q. Next we shall discuss question number 11. The question is, show that the vectors 2i minus 3j plus 4k and minus 4i plus 6j minus 8k are collinear. Here two vectors are parallel if they are scalar multiple of one another. That is, if A and B, vector A and vector B are two vectors, then if we can write it in the form vector B is equal to lambda into vector A. Lambda is a scalar quantity, so a scalar multiple of another one, lambda into vector A. Then we can say that vector A and B are parallel. Then here we have to prove that they are collinear. So parallel vectors are collinear vectors. So here vector A is equal to 2i minus 3j plus 4k we have taken, and any vector you can take as A, and if you multiply a scalar quantity with the vector A, we will get another vector as B, and that two vectors are parallel vectors. So here B I have got after multiplying minus 2 with the vector A. If I multiplied minus 2 with the vector A, minus 2 into 2, that is minus 4i, then minus 2 into minus 3, that is plus 6j, then plus 4 into minus 2, that is minus 8k cap. So here B vector is equal to minus 4i cap plus 6j cap minus 8k cap. So if you take B minus 4i cap plus 6j cap minus 8k cap, from here minus 2 we can take outside, as I have discussed to you before. If you take minus 2 common, we will get 2i cap minus 3j cap plus 4k cap. This is equal to minus 2 into, this is an A vector, that we can write it as minus 2 into A vector. That is in the form vector B is equal to lambda into vector A. Here lambda is a scalar quantity, that is lambda is equal to minus 2. So the vectors are collinear. Next, question number 13. Find the direction cosines of the vector joining the points A, 1, 2, minus 3 and B, minus 1, minus 2, 1 directed from A to B. So here there are 2 points are given to you, A, 1, 2, minus 3 and B, minus 1, minus 2, 1. First of all, we have to write vector AB. So we have already learned the formula x2 minus x1 into I cap plus y2 minus y1 into j cap plus z2 minus z1 into k cap. So x2 is minus 1, x1 is 1. So minus 1 into I cap plus here x2 is y2 is minus 2, that is minus 2, and x1 is 2. So minus 2 into j cap plus 1 minus minus 3. So 1 minus minus 3 into k cap. Let's simplify it. That is vector AB is equal to minus 1 is minus 2 I cap. Then minus 2 is minus 4 into j cap, that is minus 4 j cap. Here 1 minus minus 3. 1 minus minus 3 is plus 3, that is 1 plus 3 is 4. So 4 k cap. So AB we have got vector AB minus 2 I cap minus 4 j cap plus 4 k cap. We have to find the DCs of vector joining the points AB. So we have got vector AB, then we have to go for calculating its magnitude. That is equal to root of x square plus y square plus z square, that is minus 2 the whole square plus minus 4 the whole square plus 4 square. That is equal to minus 2 the whole square is 4, minus 4 the whole square is 16 and 4 square is 16. So we will get as root of 16 plus 16 32 plus 4 is 36. Root of 36, that is equal to 6. So the DCs or the direction cosines of AB are x divided by root of or x divided by r, that is the formula. X divided by r, here x in the sense minus 2 divided by r, the modulus of that vector, that is 6. So minus 2 divided by 6 comma y divided by r, that is minus 4 divided by 6 and z divided by r, that is 4 divided by 6. That is equal to, let's simplify it, that is here 2 cancel, that means 1 divided by 3 minus 1 divided by 3. Here also 2 can be cancelled, that is if you cancel 2 we will get as minus 2 divided by 3, and 4 by 6 if you cancel 2 we will get as 2 divided by 3. So the DCs are minus 1 by 3, minus 2 by 3 and plus 2 by 3. Next we shall discuss question number 14. Show that the vector I cap plus j cap plus k cap is equally inclined to the axis OX, OY and OZ. So we have to prove that the given vector is equally inclined to the x-axis, y-axis and z-axis. Means the angle which is formed by, or the cosine of the angles which is formed by this vector on the axis must be same, or the DCs must be same, direction cosines must be same. So let's take the given vector as A. Vector A is equal to I cap plus j cap plus k cap. Then magnitude of vector A we can calculate, that is equal to root of x square plus y square plus z square, that is root of 1 square plus 1 square plus 1 square, that is equal to root 3. Then the DCs of A we can write, that is x divided by magnitude of that particular vector, that is x is here 1 divided by root 3, y also 1, so 1 divided by root 3, and z also 1, so 1 divided by root 3. So the DCs are 1 by root 3, 1 by root 3 and 1 by root 3. So cos alpha is equal to 1 by root 3, cos beta is equal to 1 by root 3, and cos gamma is equal to 1 by root 3. These are the direction cosines. So cos values are same here. Cos alpha is also 1 by root 3, cos beta also 1 by root 3, and cos gamma also 1 by root 3. Since the cosine of angles are same, the angles must be same. That is alpha, beta and gamma must be same. So the vector is equally inclined to OX, OY and OZ. That means the vector is forming equal angles with the x-axis, y-axis and z-axis. Next, move on to question number 15. The question is, find the position vector of a point R which divides the line joining 2 points P and Q, whose position vectors are I cap plus 2j cap minus k cap and minus I cap plus j cap plus k cap respectively in the ratio 2:1. Here we have to use the section formula. Here first case is internal division and the second case is external division. So let's take the given vector as OP. OP is equal to I plus 2j minus k. Then OQ, that is minus I cap plus j cap plus k cap. Then we have learned the internal division formula, that is OR. The position vector of R is equal to MB plus NA. M into vector B plus N into vector A divided by M plus N. So the position vectors of R is OR is equal to M into B, M into the second vector plus N into the first vector divided by M plus N. Here M and N are 2 and 1. So 2 into the second vector, that is minus I cap plus j cap plus k cap plus N. N is here 1 into the first vector, that is I cap plus 2j cap minus k cap divided by M plus N. M plus 1 is 2 plus 1. Let's multiply 2 inside, that is minus 2 I cap plus 2j cap plus 2k cap plus, if you multiply 1 with the given vector, the same vector will be coming I cap plus 2j cap minus k cap divided by 2 plus 1 is 3. Let's simplify it. Minus 2i plus I, that is minus I, then 2j cap plus 2j cap, that is 4j cap, then plus 2k cap minus k cap, that is plus k cap divided by 3. That is equal to, let's split the denominator, that is 3 we can share it with I cap, j cap and k cap, that is minus 1 by 3 into I cap plus 4 by 3 into j cap plus 1 by 3 into k cap. Next is for external division. The formula is OR. Vector OR is equal to MB minus NA. M into vector B minus N into vector A divided by M minus N. So the position vector of R is OR is equal to M into vector B, second vector. So M is here 2. The second vector is minus I cap plus j cap plus k cap. Minus N is 1. N 1 into the first vector, that is I cap plus 2j cap minus k cap divided by M minus N, external division, that's why minus. So 2 minus 1. Let's go for the calculation. So 2 multiplying inside, that is minus 2i plus 2j plus 2k minus 1 multiplying inside, that is I cap plus 2j cap minus k cap. 2 minus 1 denominator come as 1. So no need to write. Go for simplification. Minus 2i minus I, that is minus 3i plus 2j minus 2j cancelled, then plus 2k cap minus into minus plus k cap, that is 2k cap plus k cap, that is equal to 3k cap. So the answer is minus 3i cap plus 3k cap. Move on to question number 16. The question is, find the position vector of the midpoint of the vector joining the points P 2, 3, 4 and Q 4, 1, minus 2. Here the midpoint formula, if a point R divides P and Q equally in the ratio 1:1, that is called R is the midpoint of PQ, then the position vector of R can be determined by using the formula a vector a plus vector b divided by 2. That is, the position vector of R is OR is equal to sum of the two vectors, that is 2i cap plus 3j cap plus 4k cap plus again 4i cap plus j cap minus 2k cap divided by 2. Denominator is 2. So that is equal to, here I, coefficient of I we can take together, or simply you can add also, no problem. So here coefficient of I cap is 2 and 4. So 2 plus 4 into I cap plus here 3 and 1 are the coefficients of j cap. So j cap into 3 plus 1 plus here 4 and here minus 2. So 4 minus 2 into k cap. That is equal to 4 plus 2 is 6 I cap, then 3 plus 1 is 4 j cap, then plus 4 minus 2, that is 2 k cap divided by 2. We can cancel 2 here, that is, if you take 2 from numerator as common, that is 3 I cap plus 2 j cap plus k cap divided by 2. The 2 numerator and denominator can be cancelled, and the final answer as 3 I cap plus 2 j cap plus k cap. Next, we shall discuss question number 17. The question is, show that the points A, B and C with position vectors, vector A is equal to 3i cap minus 4j cap minus 4k cap, vector B is equal to 2i cap minus j cap plus k cap, and vector C is equal to I cap minus 3j cap minus 5k cap, respectively form the vertices of a right angle triangle. So here, these are the position vectors. We have to prove that these position vectors form the vertices of a right angle triangle. So let's have a rough sketch of a right angle triangle. And here the plan is, we have to find out the magnitude of AB, the magnitude of BC and the magnitude of AC. And then we have to prove that this AB, BC and AC follows or satisfies the Pythagoras theorem. Then we can say that A, B and C are the vertices of a right angle triangle, or the given position vectors form the vertices of a right angle triangle. So first of all, let's go for calculating AB, vector AB. Vector AB in the sense position vector of B minus position vector of A. So let's take the coefficients together and do the calculation. Here 2B minus A, that is 2 minus 3. 2 minus 3 into I cap plus here minus 1 minus minus 4, that is minus 1 plus 4 into j. This minus is there, this minus will be going inside of vector A. So that's why here plus coming. Then the next one is 1 minus minus 4, that is 1 plus 4 into k cap. Let's go for the calculation. 2 minus 3 is minus 1. Minus 1 into I cap is minus I cap. Then minus 4 plus minus 1 plus 4 is 3. 3 into j cap. Then 1 plus 4 is 5. 5 into k cap. Then we have to go for here BC. Vector BC we have to calculate. Vector BC means position vector of C minus position vector of B. That is equal to C is this one, B is this one. Let's go for subtraction. 1 minus 2. So 1 minus 2 into I cap plus here minus 3 into minus minus 1. So minus 3 plus 1 into j cap plus last one is minus 5 minus 1. So minus 5 minus 1 into k cap. Go for the calculation. Here 1 minus 2 is minus 1 into I cap. Then minus 3 plus 1 is minus 2. Minus 2 into j cap. Then minus 5 minus 1 is minus 6 k cap. Next CA we have to calculate. CA in the sense position vector of A minus position vector of C. That is equal to A is here and C is this one. So 3 minus 1. 3 minus 1 into I cap. Then here minus 4 minus minus 3. So minus 4 plus 3 into j cap plus here it is minus 4 minus minus 5, that is plus 5. So minus 4 plus 5 into k cap. When you do the calculation, 3 minus 1 in this, 3 minus 1 is 2, 2 I cap, minus 4 plus 3 is minus 1, so minus 1 j cap, minus 4 plus 5 is 1, that is 1 into k cap is k cap. So we have got vector CA as 2 I cap minus j cap plus k cap. Then we have to go for calculating its modulus. Modulus of AB, magnitude of AB square we can calculate, because modulus of AB formula is root of x square plus y square plus z square. We want to remove that square root. So just calculate magnitude of AB square. That is equal to x square plus y square plus z square. Square root is gone because there is a square here. This is easy for us to calculate. That's why we are doing this way. So here minus 1 the whole square plus 3 the whole square plus 5 the whole square we have written here. That is equal to minus 1 whole square is 1, 3 square is 9, 5 square is 25. When you add, it becomes 35. Next is magnitude of BC square. We can calculate x square plus y square plus z square. So BC is here minus 1, minus 2, minus 6. So just to take the squares of these numbers, minus 1 the whole square plus minus 2 the whole square plus minus 6 the whole square, that is equal to 1 plus 4 plus 36. We will get the answer as 41. Next is CA, modulus of CA square, that is equal to CA, if you take, that is 2 minus 1 and 1. Just to take the squares, x square plus y square plus z square, that is 2 square plus minus 1 the whole square plus 1 square, that is equal to 4 plus 1 plus 1, that is equal to 6. Then when you check here, the highest or the longest side is BC. So because BC is more here, 41, that we can use as the hypotenuse. That is the other two sides square, that is modulus of AB square plus modulus of CA square we can calculate. That is equal to here 35 plus 6. 35 plus 6 is 41. That 41 is the square of the third side, the magnitude of the square of the third side, that is modulus of BC square. Here therefore we can conclude ABC is a right triangle. Move on to question number 18. The question is, in triangle ABC, which of the following is not true? There are 4 statements. The first statement is vector AB plus vector BC plus vector CA equal to 0 vector. Then second statement is vector AB plus vector BC minus vector AC equal to 0 vector. Then third statement is vector AB plus vector BC minus vector CA equal to 0 vector. And the fourth statement is vector AB minus vector CB plus vector CA equal to 0 vector. There is a diagram here A, B, C. So since the triangle is given to you, we can apply the triangular rule of vector addition. Let's check one by one and we will find out which one is not true. The incorrect statement we have to identify. First of all, from the given diagram we can write by using triangular law of vector addition. We can say that AB plus BC is equal to AC. So it is quite clear here, the direct by seeing the direction AB, the terminal point of AB is B and the initial point of BC is also B. So AB plus BC is equal to vector AC. So that is written here, that is from the given diagram. From here, if you take that AC, if you change the direction of AC, we know that if you want to change the direction of a vector, just to put a minus sign. That is vector AB plus vector BC equal to this vector AC, we can change the direction, then we will write as minus vector CA. Then vector AB plus vector BC plus vector CA is equal to 0 vector. So the first statement we have got, that means the first statement is a correct statement because we derived this statement from the triangular law of vector addition. So the first statement is true. Then we will go again, AB plus BC is equal to AC. Again the triangle law of vector addition. Then AB plus BC, this plus AC we are bringing to the left side, that is vector plus AC, if it comes to the left side it is minus vector AC will come, is equal to 0 vector. So here AB, BC and AC, this is the statement, second statement. So second statement also we have got, that is also true. The next one, AB plus BC plus CA equal to 0 vector. This is the first statement. Since it is true, we are using that statement. Vector AB plus vector BC plus vector CA equal to 0 vector. Then vector AB, this plus BC we are changing the direction as opposite, that is minus minus CB will come if you change the direction. So vector AB, if you change the direction of BC, it comes as minus CB plus CA is equal to 0. That is our fourth statement. You can check here, vector AB minus vector CB plus vector CA is equal to 0. So the first, second and the fourth statements are true. Of course it is the third statement will be incorrect one. So let's check it that. Here AB plus BC minus CA is equal to 0. From we can write this statement, that is vector AB plus vector BC, then vector minus CA equal to 0 vector. That is the given statement we are writing. Then let's check it what is wrong here. So here vector AC and vector CA must be equal, then only this statement must be correct, because we have already proved that vector AB plus vector BC minus vector AC equal to 0. That is the correct statement. So instead of minus vector AC, here we have minus vector CA is there. Means if this must be correct, it means vector AC and vector CA must be equal, because we have already proved that this statement is correct. So instead of this statement, if this statement we want to write in the sense AC and CA must be same, vector AC is equal to vector CA. That is vector AC is equal to, let's change the direction of this one, that is CA we can write it as vector AC, put a minus sign. So vector AC is equal to minus vector AC. That is equal to, bring this AC to the left side, that is vector AC plus vector AC is equal to 0. That is equal to 2 into vector AC is equal to 0 vector. That is vector AC is equal to 0 vector. So we got the conclusion as vector AC is a 0 vector, but here in the diagram you can check AC is having a magnitude. 0 vector in the sense the magnitude must be 0, but here AC is having a particular length, so which is not true. So the incorrect statement is the third statement, that is the question given in option C is incorrect. So the correct answer is C. So let's mark C. Move on to the last question, that is question number 19. If vector A and vector B are two collinear vectors, then which of the following are incorrect? First statement, vector B is equal to lambda into vector A for some scalar lambda. And second statement is vector A is equal to plus or minus vector B. And C, the respective components of vector A and vector B are proportional. And vector D, both the vectors vector A and vector B have same direction but different magnitudes. So from the definition itself, we know that if vector A and B are two collinear vector in the sense they must be parallel to the same line and they may have different direction and magnitude. So here the fourth statement, if you check, both the vectors vector A and vector B have same direction. So it is quite clear that something wrong with the question statement number D. Vector A and vector B may have different directions. That is what from the definition of collinear vectors we have learned. Vector A and vector B may have different directions. But here in this fourth statement it is saying that they have the same direction. So the statement D is incorrect. The correct answer is D. So let's mark D. Next we shall discuss the product of two vectors. We have learned that the product of two numbers is a number. Product of two matrices is again a matrix. But in case of multiplication of two vectors, it is defined in two ways, namely scalar or dot product where the result is a scalar, and vector or cross product where the result is a vector. First of all, let's discuss scalar or dot product of two vectors. The scalar product of two non-zero vectors, vector A and vector B, denoted by A dot B, vector A dot vector B, is defined as vector A dot vector B is equal to modulus of vector A into modulus of vector B cos theta. Simply if you say A dot B is equal to AB cos theta. So A dot B, vector A dot vector B is equal to modulus of vector A modulus of vector B into cos theta. And theta is the angle between the two vectors A and B. Here theta is the angle between vector A and B, and theta lies between 0 and pi. There are some results. The first result is vector A dot vector B is a real number. That's why it is called a scalar product. The result is a scalar quantity. Next, vector A dot B is equal to 0 if and only if vector A must be perpendicular to vector B. So vector A is perpendicular to vector B in the sense here theta becomes 90. So cos 90 is 0. That's why A dot B is also will be 0. So this is a very important result. If we want to prove that two vectors perpendicular in the sense, we have to prove that A dot B is equal to 0. The third result is if theta is equal to 0, then vector A dot vector B is equal to modulus of vector A into modulus of vector B. Next, if theta is equal to pi, then vector A dot vector B is equal to minus of modulus of vector A into modulus of vector B. Next, for mutually perpendicular unit vectors I, j and k. Here we have already discussed this I cap, j cap and k cap. I cap is a unit vector along x-axis, j cap is a unit vector along y-axis and k cap is a unit vector along z-axis. So for mutually perpendicular unit vectors I cap, j cap and k cap, we have very important results. This one, I cap dot I cap, that is I dot I is equal to j dot j is equal to k dot k. All unit vectors I cap dot I cap equal to j cap dot j cap equal to k cap dot k cap is equal to 1. Again, I cap dot j cap equal to j cap dot k cap equal to k cap dot I cap is equal to 0. This must be in cyclic order. I cap dot j cap is equal to j cap dot k cap is equal to k cap dot I cap is equal to 0. The last one, the angle between two non-zero vectors, vector A and vector B is given by cos theta is equal to vector A dot vector B divided by modulus of vector A into modulus of vector B. Next, we shall discuss the properties of scalar product. The first property is let vector A, vector B and vector C be any three vectors. Then vector A dot vector B plus vector C is equal to vector A dot vector B plus vector A dot vector C. This is called the distributive of scalar product over addition. And the next one is let vector A and vector B be any two vectors. Then vector A dot vector B is equal to vector B dot vector A. That we can say that this is a commutative property. So scalar product is commutative. And the third property is let vector A and vector B be any two vectors and lambda be any scalar. Then lambda vector A dot vector B is equal to lambda into vector A dot B is equal to A vector A dot lambda vector B. So these are the three properties we must revise. Dear students, in today's session we have discussed the remaining questions from exercise 10.2. Also we have learned the scalar product of two vectors and its properties. Hope it is clear for you all, and if you have any doubt, please note it and keep. We will discuss it during the online session. Thank you for watching.